It's especially nice for me to be able to invite you here. This is the 8th year that we have been having a public affairs forum for area high school students. And I was actually part of the very first year. I played a small part. Carol Jackson, who was then the president of the Hopewell Valley Education Association, came to me with this really great idea of trying to get students from lots of the high schools in the area to come and spend a day at the Woodrow Wilson School learning about really important issues in public and international affairs. And all I did at the time was get her connected up with the right person in the school to get this program going. I wasn't dean at the time. And then for the last 2 years, I've had the pleasure of being able to welcome you here for this day in my new role. And it's very exciting for me to do that. Now, just to show of hands, how many of you are sophomores? Some sophomores, juniors? Okay, and seniors. Seniors. Okay. So, yeah, you're on your way. You're almost done. Hang on, a couple more weeks. But I wanted to tell you a little bit about the Woodrow Wilson School in Princeton. Now, most of the seniors I know, you've made your decisions. Is anyone coming to Princeton? Maybe, okay, we have a couple. Great, good, we'll see you. But I wanted to tell you a little bit about the Woodrow Wilson School, not as advertising, although maybe a little bit of advertising. We do have graduate programs too, for those of you who are seniors. But also just to give you a sense of what happens in a School of Public and International Affairs. I think all of you will be heading to colleges all over the country, but in most places you'll have the opportunity to think about the kinds of issues that you'll discuss here today, maybe take more courses, maybe pursue graduate study in this area. And you know, it's something that I think is a great thing to think about doing. So let me just start and tell you a little bit about the Woodrow Wilson School. This is, people should know who this is. Woodrow Wilson. And Woodrow Wilson was a Princeton University president from 1902 to 1910. He went on to become governor of New Jersey, and then, as you probably know, as president of the United States. He was the one who actually coined the phrase Princeton in the nation's service. And then many years later, President Harold Shapiro added, and in the service of all nations, to really get at the idea that we consider global issues here. Okay, so here's a quiz. These are all Princeton Woodrow Wilson School graduates. So who is this? Good. This person I bet you've heard of, but you may not recognize her. Does anybody recognize her? Has anybody heard of Teach for America? Yeah, okay. So Wendy Kopp was the founder of Teach for America. Actually, the plan for Teach for America was her senior thesis at Princeton. And Teach for America is this great program that sends recent college graduates to work in schools, underserved schools all across the country. And it's becoming an incredibly coveted job after graduation. Students really like to do this. So it's something, again, that you might think about in the future. Okay, who's this? Okay, good. David Petraeus, yes. Soon to be CIA chief. And this is somebody you may not recognize, but I bet you might hear a lot about soon. Anybody know?
Mitch Daniels.
Mitch Daniels. Okay, so Mitch Daniels is currently governor of Indiana, but he's somebody who may soon declare to be a candidate for president running in the Republican Party. So those are the only people that I want to go through. But I guess what I want to do is close just by, telling you a little bit about, you'll hear more about what you're going to do today specifically, but I hope that this gives you a flavor of what you can learn if you decide to pursue public or international affairs in college or in graduate school. And I hope you find it interesting and enjoyable. I think the question that you're going to deal with today, which is nuclear energy policy in New Jersey, is very interesting. This is something that has come to national attention due to this, triple devastating earthquake, tsunami, and now nuclear crisis in Japan. And it's prompting a lot of countries, including the US, to take a hard look at nuclear energy and the safety of nuclear power. And so this is the question that we're going to ask you to address today. So I will end there and turn it over to our Assistant Dean, Elizabeth Donahue, who has taken the lead in really planning the day's events, and she'll introduce the faculty panel who will be speaking to you. So thanks a lot, and have fun.
Hi, welcome. So I want to take a little bit just to take you through today and so show you what you can expect. As Dean Paxson said, we're really going to give you a crash course in public policy making. We talked a lot about what we wanted to do today, and it struck a lot of us that just talking at you can sometimes make you wish you were outside on this gorgeous day. So we wanted to make it a little bit more interactive, and so we are really doing what we do for our students in 12 weeks in 6 hours today. In some ways, then, this is going to be an artificial exercise, but in some ways, it's actually more of a real-life exercise. Real-life public policy makers often have the benefit of a staff person coming in, talking at them for an hour, and then the policymaker going to the floor of the Senate or the House of Representatives or the New Jersey legislature and really having to defend a policy on not a huge amount of information. And so in some ways what we're doing today is more akin to real life than what we do with our grad students and undergrads here. So we tried to think of an issue that really has resonance both because it's on the front page of the newspapers, but also because it has resonance for you living here in New Jersey. And as you'll hear when the speakers start, nuclear energy and the potential pitfalls and positives of it are not something that are just in Russia or Japan or in other countries. They're very much something that affects you here in New Jersey. And we have one slide in particular that will show you how much this really affects your day-to-day life. And again, just to sort of point out how real this is, there's a task force in New Jersey right now who's been charged with thinking through what the state is going to do on this issue. So this is not a pretend topic. It's something that is very much real and brought home even more because of the crisis that just happened in Japan. So let me take you through the agenda. You have it all in front of you, and you all have mysterious little numbers in the corner, so I'll explain what those are. So what we're going to do for the next couple hours is really just fill your head with information. And what we've tried to do is we have 4 faculty members here who I have to give a huge thank you to because they've given a lot of time, not just in being here today, but also in helping us think through what today is going to look like. And we're in reading period right now. These guys don't have to be here. And so, especially I sort of wish it was raining outside, you know. But anyway, so I want to really say a huge thank you to our faculty for giving their time today. And they're going to take you through all the different elements of what a New Jersey legislator who's really trying to think through this would have to think about. They'd have to think about the energy issues. They'd have to think as opposed to other energy sources. They'd have to think through the economic issues. They'd have to think through the safety issues, especially, again, given what we've just learned about Japan and in the anniversary of Chernobyl. And they really have to think through, not just the safety issues, but the health ramifications of those safety issues. So those are all pieces of a public policy pie, if you will, that they're going to try to give you information on. I think because of the time, we are going to just have the 4 of them present and then have the Q&A at the end. So we're going to ask that you keep your questions as you go, and then we'll have some time period to do that. But one of the things they've done, which has been very, very helpful, is as you see attached to the agenda are a set of questions that each of the presenters have put together. And this is really a study guide to help you go through, and it's not a test, we're not going to ask for these at the end, but if you can take a look at the questions, it will help you in your note-taking and your thinking about this issue. And the reason that you should take notes is at the break, at lunchtime, we're going to get your lunches, and then we're going to break into 5 groups, and you're going to go with your number, okay? And we're going to go into 5 different classrooms, and we're going to have a working lunch. We're not wasting any time here. I don't dare let you guys go out by the fountain. We'll never get you back. So we're going to break up, and you're going to go with your, 1, 2, 3, 4, 5. We've tried to do it in a way that schools are not all together. You won't be all, just with your classmates. You'll be with people from other schools, which I think is another good real-life exercise. And at that point, You will sit, we have MPA students, our master's students have volunteered their afternoon to come and work with you, and also people from the Public and External Affairs group that's here today. And you will be charged in your group with coming up with a memo of sorts. So you are working for a New Jersey legislature, your boss is in the New Jersey legislature, or you can pretend you work for the governor, but you're going to go and you have to give recommendations about what New Jersey should do about nuclear energy today, given its current situation, and what its future plans should be. And then we're going to regroup back here, and you're going to do your presentations. And so when you gather, there's going to be a lot of you. You're probably going to want to choose one or two spokespeople to give your presentation. So that's all I'm going to say. Are there any questions about how today is going to run? No? Everyone's clear? We have lots of free pens if anyone needs a pen. Okay, so let's get started. The first people we're going to hear from are Alexander Glazer, who is the assistant professor at the Woodrow Wilson School and in the Department of Mechanical and Aerospace Engineering, who's a great example of how you can combine public policy with science. And M.V. Ramana, who's an associate research scholar at the school's program on science and global security, and they're going to address the important issue of everything you want to know about nuclear energy but were afraid to ask. Then we're going to hear from Eric Larson, who's a research engineer at the Princeton Environmental Institute and a lecturer in mechanical and aerospace engineering, and he's going to look at nuclear in New Jersey, status and alternatives. And then finally, we're going to hear from Laura Kahn, who's a medical doctor, as well as a research scholar at the Program on Science and Global Security at the Woodrow Wilson School, and the mother of a Princeton 11th grader, Princeton High School 11th grader. And she's going to address the issue of leadership, crises, and nuclear reactor accidents, health, and public safety concerns. So with that, I'm going to stop speaking, and we'll start the program. Thanks.
Welcome, everyone. I'm Alex Glazer. I give kind of the brief, first broad overview, and as you can see, I simplified the title a little bit. I thought it's maybe a bit too ambitious to answer all the questions you may have had in 10 or 15 minutes or so. So it's an introduction to nuclear energy, and I start very broadly, and then my colleagues go into more and more detail and more of the local issues. So what is this about today? I guess what we're really talking about, of course, is the future of energy. And in the midterm or in the short term, we have to move away from fossil fuels. And as you can see here on the slide, this is a quote from the President's State of the Union address earlier this year. He has proposed a clean energy standard, and the objective is to move away from fossil fuels and non-clean energy sources by 2035, and get 80% of the U.S. electricity from clean energy sources. Now, some of these sources are really kind of no-brainers. There will be more wind, there will be more solar, but some others, including nuclear, are more controversial. And I guess that's really the topic of our task force today. As you can read here, the president still thinks that nuclear has to be on the table. It is a serious option, and he kind of even re-emphasized this in a speech that he gave more recently after Fukushima. He said, yes, even with the Fukushima experience, we still have to have a serious look at nuclear energy. So, as I said, what I try to do in 5 or 10 minutes is kind of introduce, what is nuclear power, and I guess there's no way you can kind of avoid it, but I hope that it's still of interest to you. So there are two ways, two variants of nuclear power. One is nuclear fusion, which is what happens in the sun. It's very difficult to pull off on Earth, even though people are working on it. And the other way is nuclear fission, which is, really, as you can see here in this cartoon, splitting an atom. So you see uranium nucleus here. If it's hit by a neutron, there's a certain chance that it will break apart into two fragments almost equal size. And these two positively charged nuclei are sitting next to each other and then repel each other because they're positively charged. And this releases energy in the form of heat. And what you can also see here in the process, you're also emitting two or more new neutrons. And if you think about this, well, if you kind of put enough material together, you can get a chain reaction. And that's, that process was discovered in the mid-1930s in Nazi Germany, just before World War II started, by Lise Meitner, who then had to actually leave Germany shortly after, Otto Hahn and Fritz Strassmann. So that's the basics. And very quickly it became clear that this is potentially a major source of energy. And here, of course, you can't read the letter, but you may have heard about this letter. This is a letter that Einstein wrote not too far away from here in August 1939 to President Roosevelt, in which he said, and you can read it, there may be the possibility of a chain reaction. You do release vast amounts of energy, and it appears almost certain that this could be achieved in the immediate future, and it would also lead to the construction of bombs. This was it was basically the start of the U.S. Weapons program during World War II. And it turned out Einstein was correct. It was not that easy as you may have thought in '39. It took the Manhattan Project and a 3-year project basically to develop nuclear weapons, but you need only a few kilograms of nuclear material, either highly enriched uranium, and we're not going to go into all these details, or plutonium to make a nuclear weapon. And you see here the amount of plutonium it took to build the Nagasaki weapon. And just to give you an idea of the destructive power of a nuclear weapon, the Nagasaki and the Hiroshima bomb had a yield of 20,000 tons of TNT, 20 kilotons. And you see here the circle just to give you an impression of the size of the area that would be, has been destroyed in Hiroshima and Nagasaki as a result of the air blast that you get when you explode such a weapon. These are the early weapons, and as you know, afterwards, after World War II, there was the arms race, and more states developed nuclear weapons, and also larger nuclear weapons. And you see the area of destruction that correspond to these weapons in this cartoon here. So now moving away from the weapons, I just wanted to emphasize this is where it really came from. But there are other applications for nuclear energy. And second, I should also emphasize, we started to build nuclear reactors also during the war, not to make energy, but to produce plutonium, which can be used in nuclear weapons. So the very first reactors here in Chicago in 1942, and then later on the West Coast in 1944, were used to make plutonium for weapons purposes. These are the very first reactors. Then came another type of reactor, again, not for electricity, but to power nuclear submarines. It's a very appealing kind of idea to use nuclear reactors for that purpose. You don't need oxygen to run them, so you can essentially have your submarine, traveling underwater for indefinitely, and you need very little fuel, so you can stay out on sea basically, essentially forever. So that was a very appealing, of course, feature for the military. So the nuclear-powered submarines really came next in the early 1950s. And then finally, people thought, there must be something useful that we can do with this technology, peaceful application. And we started building nuclear power reactors. And the first reactor was actually built here in Pennsylvania, not here in Pennsylvania, but not too far away in Pennsylvania. And it was a clone of a submarine reactor. And it was the Shippingport Atomic Power Station in 1957. And as you will see in a minute, of course, you need very little material or fuel to run a nuclear reactor. And initially people thought, and here's a quote by the chairman of the Atomic Energy Commission at the time from 1954, and you may have heard this quote. People make fun of it today because it turned out nuclear technology is actually very complex. It's not inexpensive, but back then it was plausible to assume it may be too cheap to meter. I mean, if your fuel is essentially free and abundant, then electricity may be really too cheap to meter. And you can read the quote here. And just to put this into perspective, here you see the amount of fuel you need to, say, fuel a certain number of US households. You need 200 tons of uranium. You have to mine those, and you fabricate this uranium, 200 tons, into 20 tons of fuel. This is what a nuclear reactor needs every year to operate. And only a small fraction of that fuel is actually fission in the process. Only 1 ton of fuel is fission, and that's the small bullet here. And that compares to, it's unbelievable if you kind of have them next to each other, 3 million tons of coal, which is 15,000 times more. And so just as a heads up, so we're going to talk a bit more about New Jersey today. New Jersey has 4 nuclear power plants. 3 of them are kind of co-located in the south of New Jersey, Hope Creek, and the 2 Salem reactors. And I couldn't find a better picture, but here they are. And you can spot the 3 domes, sitting close to each other near the shore. And I should, also mention one of them, the one that's kind of sitting alone there next to the rectangular building, is essentially a copy of the Fukushima reactor. It's exactly the same design that was destroyed in the Fukushima accident. So these are very old reactors, or some of them are very old. And we'll get to that question during the course of the day, what to do with these very old facilities. Just so that you've seen it, this is how a nuclear reactor would, in principle look like. This, again, a cartoon. And a cynic would say it's just a very complicated way of boiling water. You have, the fuel, the nuclear fuel, you put it close together, and it's called the reactor core. You put it in a vessel filled with water, and the chain reactions, the nuclear chain reactions will heat the water, and you kind of use that hot water to generate steam, and the steam drives a turbine, and the turbine drives a generator. And that's basically it. And of course, the problem is that you create a lot of radioactivity in this process. You have to be very careful. You build a containment structure around it, and you have control rods in place to really kind of manage your chain reaction and make sure it's not, going to explode. So that's basically it. And I don't think we need to know, much more about how a reactor exactly works, but here you go. And so, I already mentioned, in the 1950s, we started kind of building these reactors in the 1950s, 1960s. There was a real boom in the early 70s before the accidents at 3 Mile Island and Chernobyl really kind of ended kind of global interest in nuclear energy. And it basically has been sitting at this level now for 20 years. 440 reactors, 4 have been destroyed recently in 30 countries, and they provide about 14% of global electricity. It actually should be a bit lower now, since Japan has lost a few reactors, and Germany, as you may have heard, has basically shut down half of its nuclear fleet in response to the accident. And I just read this morning it's probably going to be permanent, that these 8 reactors actually will remain shut down. So this is, I think, I'm coming already to my end here, but I have 2 questions for you. Let's see if we can come up with a few answers. We really haven't told you that much, but you may have already some ideas about what makes nuclear energy kind of special. So I have 2 questions for you. One is, what factors tend to put nuclear power at an advantage, and the second one will be what factors tend to put nuclear power at a disadvantage. Any suggestions here in the audience? Yeah, just go ahead and
it's pretty clean aside from the fuel storage when it's done, but as they're producing it, doesn't set up fossil fuel. There's no carbon emitter or anything, so it's a pretty clean source of energy.
Okay, so point 1, and that's quite honestly, I think, the only reason why we revisit nuclear energy today. It's clean as long as you don't have accidents. But it's definitely low carbon. There are essentially no CO2 emissions. I mean, on a life cycle basis, maybe 10% of what a coal plant would have been. So that's kind of reason number one why we actually, basically sitting here and talk about nuclear energy. Anything else? Yeah, I see a couple in the chair. Just speak up.
Produce a large amount of energy.
Right. So it's an important point. As I mentioned, probably you need you don't need a lot of fuel. And basically, if you look at uranium resources, it essentially means, for all practical purposes, it's there's a lot of uranium out there, and for the next 100 years or so, we wouldn't have any problem, fueling any nuclear fleet we'd like to. So there's a lot of fuel. There are very few little CO2 emissions. I had one more over there.
Just should say efficiency.
Okay. Anyone else? Yep.
I think there's two things that lend nuclear security or nuclear technology an advantage. The first would be security, like the advantage of an uninterrupted energy supply that can be made domestically would be very politically expedient. And also, in the eyes of other nations, having a developed nuclear program would be a strong plus when you're dealing with other nations in international politics.
Okay. Well, I'm not sure if everyone's heard it. I guess it was, well said. And energy security is a very important argument, especially for the U.S. debate. But it's still important to remember, though, that for some countries like Japan or China, it may actually be less of an argument. I mean, if you have to have a lot of uranium, either you have it or your friends have it, and that's true for the U.S., where uranium comes from Australia, it comes from Canada, so friendly places, and that's kind of one important argument. But it's not true for everyone. But I take your point; it's a valid argument. Okay, one more, or. Not sure. Okay, let's see what I have on my list. I had time tested. We've been using it for 50, 60 years, and it's been working. So in principle, we know if we wanted to build more nuclear power, we just, we could do it. So it's time tested. We have the CO2 emissions. In principle, we're going to talk about this more later on, but there are really no limits. I mean, if you want to build 1,000 gigawatts, you build 1,000 gigawatts. I mean, you can technically do it. There are few physical constraints. That's maybe not true for all renewables. We have the resources. There are few resource constraints. Usually you run a nuclear power plant 90% of the time. Because it's very expensive to build it, and once you have it, you really want to run it all the time. And it's good for baseload electricity generation. And again, if we talk about wind or solar PV, there's the issue of intermittency, and we'll get to that later on. And you can produce it centralized, which is good for the grid that we have today. It's a minor point. There's one more point that's actually very important, maybe more subtle, I guess. That's this one. Nuclear is very appealing if you think you need a lot of energy. And it's a chicken-egg thing in a way. So if you think you need a lot of energy in the future, you kind of automatically come back and say, well, maybe we should go for nuclear. So it becomes almost an automatism. If you think, I don't have nuclear for whatever reason, you may think about a very different future. You think, well, maybe I should really focus hard on energy efficiency. And that's kind of an argument. It's a bit more tricky to address, I think. Once you take nuclear off the table, you really think very hard about energy efficiency and really try to bring your projections down. Okay, so one more slide. What are the disadvantages? Now I see more hands coming up. Okay, in the back.
The things that are produced from the process are dangerous and need to be taken care of in very specific manners. That's very difficult.
Right. So there's the whole big issue of waste disposal. We have lots of radioactive waste, about 20 tons of spent fuel every year. We have to do something with it. The idea was to put it into Yucca Mountain. And that project is essentially now dead. We've spent almost $10 billion on it. The Blue Ribbon Commission, which has been established by the president, will come out later this spring and make recommendations how to move forward. So spent fuel disposal is a big issue, as you may all know, I guess. Yeah. Just speak up.
other than like the nuclear waste it produces, it also, there's only so much nuclear uranium out there. Like you said, only enough for about like the next 50 to 100 years. Also, the nuclear power plants that like they don't just show up overnight. It takes like a decade to build them. So it's not realistic to do it like right now. But it would be it would be useful in a plan for like long term, I guess.
Okay, no, it's a good point. You know, but it's hard to. You have to come there. You have to get there. You have to scale up. And in terms of, you can frame it in terms of economics, I guess. You know, long construction times are just something investors don't like. And I have the economics kind of at the bottom of my list. It can basically go either way. It can be favorable. It can be a disadvantage. Right now, it actually looks. You know, people are afraid that nuclear after Fukushima may not be so appealing because it's very, you know, uncertain how the NRC will respond to it and how difficult it will be to actually build a nuclear power plant on budget and on time. It's a good point. Okay, I have more. In the back.
I think the packet might mention it, but the cost of preventative measures too. So, like ensuring that things like what happened in Japan don't happen again. Different kind of prices.
You talking about accidents, I guess, or
yeah, preventative measures. So, you know, putting in effort when there's a high risk of something happening, but you sort of need to do that.
Yeah, well, you know, of course. I mean, accidents are, you know, big. One of the, you know, the most unique and most serious arguments, and you know, I fully agree. And I guess Ramana will cover this aspect. Let me just run. I have one more. Let's take one more.
There's always the possibility that countries with nuclear plants could be enriching uranium for dirty bombs.
Right. So that's the whole nuclear proliferation issue. There's also a risk of, you know, nuclear terrorism, radiological terrorism, and so on. So that's kind of one additional unique aspect. And I have one more here in the front.
I just want to say, in the event of any sort of catastrophic failure, there's a very real health risks that can never need a needed area.
Right. Oh, that's really why we care about, you know, I guess the risk of reactor accidents, and both Ramana and Laura will kind of have, you know, the whole talk on this. Okay, let me just quickly wrap up here. Risk of catastrophic accidents. We have to take care of the nuclear waste. I think you got everything. The weapons connection. Of course, and that's the way I started. For many or for some countries, it's actually a convenient way to get into, at least get a weapons option in, you know, hiding behind a civilian nuclear power program. We had you know, the risk of nuclear terrorism, where you can have, you know, you can actually sabotage a nuclear power plant. You can fly an aircraft into a nuclear power plant. And then, you know, actually that wasn't mentioned. Public opinion is a big deal, and I guess we'll talk about that a bit more. I mean, public opinion against wind is kind of, it's not such a big deal, but, you know, nuclear is very different. And, you know, in Europe, for instance, in Germany, it really dropped to an all-time low after Fukushima. And essentially 90% of the public now are favorable in terms of, you know, support the phase-out of nuclear energy. Economics, we've mentioned, it really can go either way. It doesn't look very good right now for nuclear. But, you know, you can build cheap nuclear if you don't care about safety, I guess. And we had the energy security argument. So you have everything. Okay, let me just skip this. And I have only 2 more slides. I mean, one issue that I briefly mentioned in the beginning, here you see who's using nuclear power today, you know, the list of countries. And I'm not sure, can you see it? The light gray kind of shows you the fraction of the facilities, or the number of facilities that are, you know, old, 40 years old. And we initially thought at this point we're going to retire them. And there's 78 out of 440 that are now very old, and we think about relicensing them, and especially those in particular also those in New Jersey. Hope Creek and Oyster Creek are essentially 40 years old, and we think, and essentially that's the plan, to give them another 20 years and maybe another 40 years. So we've been working with technology that's really not state-of-the-art. Is this the right way to go or not? Is the question. So here's my final slide, and I think that's the one Elizabeth wanted to see. Here it is. This is New Jersey, and, you know, the east coast of the U.S., and I just plotted here the nuclear power plants that are closest to us, and here you can see kind of areas you should be worried about. And so you are here, And if there's an accident in one of those power plants, and it doesn't matter where the wind blows, it's probably one of them would be, well, you know, assuming that every reactor, I guess, has an accident at the same time. But we're not in a very good spot here. So the 10-mile radius here, the smaller circle, is the one, and I think Laura will talk about this. This is the so-called emergency planning zone. There, you know, you have to test radioactive pills, you would have to evacuate, and so on. That's really surrounding the power plant. What is interesting, when Fukushima happened, there was a cable by the US Embassy sent to US citizens in Japan and recommended for US citizens to evacuate within 50 miles of the Fukushima reactors. And I mean, it gives you a sense, and many people thought it was not a good idea to actually give that recommendation, because I might show the slide here. You know, if you put it on the slide of New Jersey, you think, well, that's pretty, what does it mean? You know, if Indian Point has a problem, you would have to evacuate New York City, which I guess everyone knows it's just impossible. Okay, and that's, I think, all I have. And we move on with Ramana.
Just something to keep in mind from the last slide that you saw. Not all those plants were in New Jersey, right? So that's going to be an issue when you're thinking of public policy issues, that some of the plants are in New Jersey, some are in your jurisdiction, and some of them aren't. Okay, so just tuck that away.
I missed it.
Thank you. So I guess I'm going to be playing Cassandra here, and I'm going to talk more about the kinds of things you're really afraid to talk about. And I'm going to focus mostly on the three of the disadvantages that Alex mentioned. And in particular, I'm going to talk about the question of safety, because that's sort of what's driving all the attention towards nuclear power today in the aftermath of Fukushima. And we just had, you know, about 10 days ago, the 25th anniversary of Chernobyl. And then I'll talk a little bit about public opinion and the question of nuclear waste. So, as most of you know, nuclear reactors are capable of catastrophic accidents. There are also occasionally accidents involving other facilities that are part of the nuclear fuel chain. So for example, we've had accidents involving waste tanks and uranium enrichment facilities and so on and so forth. But reactors are usually the most focus of most of the attention. This characteristic is unique to nuclear power among all electricity generation technologies. This is not to say that other technologies cannot have accidents, but the impacts of those, in the case of nuclear power, sort of can spread over a very large area and can also have very long-term effects. So in some sense, spread out over space and time. And so that's a picture of Chernobyl. So why are we concerned about accidents, apart from the fact that we've seen multiple accidents at Fukushima recently? The reason is you can think of it in terms of two categories. The hardware that's associated with nuclear power, the technology itself, and what one might call the software, the who has to operate it and so on. So in terms of the technology itself, some of the characteristics are that if you saw the picture that Alex showed of a reactor, it's a fairly complicated beast. And that's actually a cartoon picture. A real one looks even more complicated. And so these are very complex systems. And different parts of it can be doing different things and affect each other. And if you look at any reactor accident, you find that various parts which we sort of expect to behave in certain ways actually end up doing things. The second is that they contain large quantities of radioactive materials, and radioactive materials are hazardous to health. And thirdly, many of these reactors operate at either high temperatures or at high pressures. So in the kind of reactor design that is used in nuclear submarines, for example, the water that's used to cool the reactor and to slow down neutrons is kept under very high pressure. So you have a high pressure vessel in which it's this thing so that it doesn't boil away. Whereas in the case of the Fukushima reactors, for example, these are boiling water reactors, so the water starts boiling because it becomes hot. In principle, in one of these accidents, there are large energy releases that are possible, and so you could have explosive releases in some cases. And finally, reactors operate at very short time scales. Things can spin out of control very, very fast. At Chernobyl, for example, the time between the first sign of the accident, when one of the things in the control room sort of gave a sign there was going to be an accident, and the first explosion was 90 seconds. So there's absolutely no time to react in some of these cases. Fukushima, on the other hand, we've seen it sort of happen over a much longer period of time, but in front of TV cameras for the most part. In terms of not just the technology, but in terms of what else goes into running a reactor, you have to remember that all these reactors are operated by people and also designed by people. And in most cases, you find that they are capable of making errors. I'm going to say errors in some quotes, because what you often find is that when an accident happens, and if you ask any of these operators later on, why did you do a certain thing, they often have a very coherent picture for why they acted in a certain way. And the reason why it led to this particular consequence was not something they had foreseen, and this goes back to the question of how complex the technology is and how difficult it is to envision what might go wrong. So the operator might be thinking, I'm doing exactly what I'm supposed to be doing in a given situation, but it leads to a result which you don't expect. And likewise, in the case of the Fukushima reactor, for example, one of the problems, as I'll talk about later, was that the electrical switchyard where the backup generators are connected to cool to a cooling circuit was kept at a low level, presumably because they wanted to avoid other vulnerabilities like fires or something, but it got flooded in the case of the tsunami. And the designer presumably didn't expect this tsunami to be so high, and so you have these kind of errors which come to bite you back. And secondly, you also find that because these operators have to act in very specified ways, they have to be very tight organizational requirements. And so the question that comes up is, how do you actually ensure that a huge organization involving hundreds or thousands of people actually act in very prescribed ways, and sometimes these prescribed ways may not envision what might be happening. All right, what do I mean? So what do designers and engineers do about this? So what they try to do is to say, we know this is a hazardous technology that is capable of accidents, but we will try to put in safety features that can protect against an accident. And so what they try to do is to put in multiple protective systems, often redundant, so that if one fails, one doesn't actually operate the way it's supposed to be operating, then maybe something else can take over. And so many have to fail before there is a radioactive release. This term is often, this feature is often called defense in depth. And for example, so if you look at this picture there, you have the uranium and the fission products, the things which are created when the uranium fissions. These are the ones which are really, really radioactive. Those things sit inside this fuel rod, which is usually covered with some metal cladding, zirconium or stainless steel. And then that's kept inside a fuel assembly, which is kept inside a reactor vessel, which is a pressurized vessel, so it cannot explode very easily. It can sort of withstand high pressures. And then there's presumably an outer containment building, a concrete containment building typically, or steel and concrete. So all of these multiple things have to be breached before the radioactivity actually escapes out into the biosphere. The problem is that multiple systems do fail on occasion. So in the case of Fukushima, for example, one particular cause, namely the tsunami, took out a whole bunch of these protective systems at the same time. So first, the reactor lost the electricity to it from the outside grid. Then the second was that the oil tanks, which are used to fuel the diesel generators, they were washed away. Third, the switchyard where, as I mentioned, where the electricity connection to the reactor is connected, that got flooded. And it's also probable that the water that's ultimately sort of going to come into the reactor to cool, which comes from the ocean and takes back the heat into the ocean. So the ocean is the one which is acting as a kind of heat sink, as it were. That may have also been damaged. So, but the thing to remember though is that, so in one particular accident, you can imagine that a number of safety systems can fail at the same time. But also one should remember that, so one of the lessons which a lot of people have been sort of taking is, oh, the tsunami was the problem. But if you look at other earlier reactors, there was no tsunami in the case of Chernobyl or in the case of 3 Mile Island. These were purely internal events. There was no external accident that kind of drove this. So just saying that, no, this reactor is safe because it's far away from the ocean and is not vulnerable to a tsunami is a wrong lesson to learn. As I mentioned, there are also challenges because of the fact that these reactors have to be operated by people. So this picture, for example, is actually the picture of the control room in Chernobyl. But this is the Chernobyl 1 reactor, this which is operating is not Chernobyl 4. But you can sort of see how complicated that thing is. There are so many gauges and so many valves, a few sort of operators sitting there trying to make sense of what's going on there. It's an extremely difficult situation in case of an accident. And in the case of Chernobyl, what happened was that they were actually trying to carry out an experiment which was trying to enhance, to test the safety of the reactor. It was a badly conceived experiment in some sense, and so it went really badly wrong. But how do you sort of ensure that operators don't act in these kinds of ways? It's very, very difficult. Because they ultimately have a lot of control over what the reactor is going at any given point of time. The other thing you might have noticed in some of the news reports following Fukushima is that there are lots of stories about how bad the Japanese regulatory regime has been, that they've been making violations of rules in various cases, and somebody has to be sort of sitting there making sure that they don't do that, and that has not been happening. So the question is, how do you not just design for safety, but ensure that safety is actually going to be there? And this is a very, very difficult challenge. So the implications of these sort of features seems to be that accidents are going to be inevitable at these kind of reactors, even if they are rare, even if they are low in frequency. There are designs which are newer, which have been designed after Chernobyl, for example, which have greater safety features. Now, whether these safety features will actually prevent an accident like Fukushima or not is an open question. There have been claims and counterclaims. But what one can say is that some of the newer designs that have been engineered for greater safety are definitely more expensive. And so to put more safety systems makes it more expensive, and nuclear power, as you know, is already quite expensive. And the economics of it has not been particularly conducive for a vast expansion. What happens if there's an accident like this? We'll hear more about this from Laura, so I'm not going to sort of talk about it in great detail. But as I mentioned in my first picture, there are radioactivity fallout has sort of all over Europe resulted from Chernobyl. So it's something which has very large-scale consequences. What you should also notice is that there are sort of isolated spots where the radiation levels have been much higher than the others. And this is actually a function of the fact that this radiation comes down because of rain and other weather conditions in specific places. And so there are impacts of this which are local. The primary impact, of course, is very close to the reactor. And so the people who live near any reactor, in a sense, are the ones who are subject to much greater risk. Whether there's an accident or not, they live with the risk. Whereas the benefits of nuclear power, as it were, sort of flow to a much larger society, right? So there is this whole question of distributive justice, right? Who is bearing the risk and who is getting the benefit? The second implication is that regardless of whether there is going to be external health implications or not, for the companies that run these nuclear reactors, or for the organizations that run the nuclear reactors, it could be a very, very expensive proposition. the Tokyo Electric Power Company, which runs Fukushima, is sort of in danger of going bankrupt, and the Japanese government is going to come in to bail them out and so on. And here's a quote from a former US Nuclear Regulatory Commission member called Peter Bradford, who talked about how Wall Street has generally reacted to accidents. And you find that typically those nuclear utilities that actually decide to construct nuclear power plants have their credit ratings go down typically. And this is both a function of the fact that you have this long-term construction project, and so money is going to be sunk down there, and there are uncertainties in how long it will take, but also the fact that you are incurring the possible risk of a major accident. You also find, as I mentioned, that when you look at the cost of nuclear power plants, you find that in the United States, the blue dots are the ones which are in the US. And you see that just after 1979, when 3 Mile Island happened, you see that the cost of nuclear power sort of goes up much more rapidly. The other picture there is, other curve there is for France. And what's also interesting is that even in the case of France, you see that the costs have been generally going up over a period of time. So this has sort of implications for economics. I'm not going to talk about that. Eric is going to talk about it much more. But what I'm most interested in here is the fact that when you have accidents, you have implications for economics. It also sort of affected reactor construction rates. So you see that if you look at the global reactor construction, it falls very drastically after Chernobyl. And this has been one reason why, if you look at projections of nuclear power, so the curves that you see saying 73, 77, and 82 are the projections for how much nuclear power there was going to be in the future. So this is what they thought would be the actual amount of construction, and the curve in the bottom right is the rate at which actually it is constructed. So there's a huge sort of gap between what has been expected of nuclear power and what is actually delivered. The other sort of disadvantages that Alex mentioned is the question of public opinion. In general, it might be said that public opinion is not very favorable to construction of new nuclear reactors, but it's not necessarily supportive of phase out either. Now, this is a depends very much on geography. There are different countries that are very, very different. So, for example, if you look at this survey, this was by Accenture. They asked, do you think your country should increase its nuclear electricity generation capacity or start using? And you find that there's about a third roughly, or maybe a half, saying yes, definitely, and another saying yes, but only if my concerns are overcome. And every public opinion poll is sort of different, because the answers that people give are typically dependent on what they've been pumped up with earlier. So if you sort of talk about nuclear power as being one of the source of energy security or of saving us from climate change, people are much more supportive of it. Whereas you talk them up about saying how hazardous it is, we just had Fukushima, and people, so the numbers go down. But nevertheless, sort of broadly speaking, one can say there's roughly 3 categories of people: some who are highly supportive, some who are highly critical, and some who are in the middle who sort of say, look, let's keep what we have. We don't want to waste the money that's been spent, but let's not build more of these things. But when you actually come to trying to construct a nuclear plant and you say, here's a specific location where you're going to build it, would you like it in your neighborhood, so to say? And the numbers again change. This is sort of, so that's, you can take it for what it's worth. The nuclear power is also one of the few things where you have mass movements basically calling for stopping it. So these are pictures from around the world. So the picture on the top left is from Germany from last year. And this is about nuclear waste disposal. The other 3 pictures are from, on the one on that side is from Barcelona, Spain. This is from Tokyo, the one on the bottom left, and this one is 3 Mile Island, Pennsylvania. And so this is one of those technologies that actually evoke very strong emotional responses from people. Why is there this opposition? In part because people have very strongly negative perceptions of nuclear power. So if you look at people, and people have sort of done research for 20 years, or 30 years actually now, asking people, what do you associate with nuclear power? What do you think of nuclear power? And just on a whole bunch of other technologies. And you find that there are various things that people associate with different technologies. It could be dangerous, it's fatal, it's dreaded, it's catastrophic, it has implications for future generations, and these are things which are typically considered bad. Similarly, things where I don't have control over the risk that I have. It's very different from, people often talk about how the risk from a nuclear reactor accident is much, much lower compared to, let's say, an accident on the road. But people typically say, look, I drive carefully, I have control over what my risk of an accident in a car is. I have some control, if not complete control. Whereas in the case of, what's happening in Oyster Creek, I have no clue. So there's a huge difference in how people perceive risks from these things. And so, different things, all of these are, potentially hazardous, but people have sort of think about it very, very differently. So in that sense, it's it's something which actually puzzles a lot of the technically trained people, the physicists and engineers and so on, who tend to think of risk as the probability of an accident times the impact of an accident, but people don't think that way. They kind of think of hazard rather than of risk, but also different characteristics of the hazard. So it's very difficult to sort of say this one is more hazardous than that, because there are multiple properties that come with different things. And so Paul Slovic, who's one of the sort of founders of this field, who sort of went around, a social psychologist based in Oregon, he has this, he mentioned this at one point, that in the risk perception literature, nuclear power has a special distinction, that it is the one with the most negative and most problematic constellation of traits. And so for various reasons, it's something which the public is really reluctant to sort of have, especially when it comes to sort of facilities where they may be at risk of suffering from an accident. One point which I would mention is that the concern is not necessarily that of radiation, as many people assume, because people seem to be quite okay with having X-rays and other kinds of things where they see a very direct benefit to them. And they're not sort of really dreading radiation per se. But these are it's different. The last point which I would sort of mention, which somebody mentioned from the audience, is that nuclear power is also unique in that it produces nuclear waste, which is hazardous to human health for hundreds of thousands of years. And this is the reason why many, many countries have sort of thought about how to dispose it off. And the solution that most countries have sort of decided on is to bury it deep somewhere in a geological repository. In the case of the United States, the picture here shows that of a mountain called Yucca Mountain. It's in Nevada. And the idea is that you would take, over a period of maybe decades or centuries, you would sort of entomb all the waste in sort of tunnels there, and then hopefully you want it to sort of stay without the radiation coming into contact with human health over a period of hundreds of thousands of years, if not millions of years. And this is an extremely, this is completely unprecedented. You've never sort of had to deal with things which you have to plan for hundreds of thousands of years. And the task is somewhat impossible because you have so many uncertainties about what's going to happen. Is there going to be a volcano there? Is there going to be an earthquake? What are the kind of future geological patterns? What's going to be the patterns of how people will use water? How will they use the land? We have no idea about these kinds of things. Partly because of these kind of challenges, but also partly because of the sort of negative associations related to nuclear waste, most countries have had a very difficult time trying to find a site. The only two countries which have sort of identified sites so far are Sweden and Finland, and they're still in the early stages of actually trying to construct one of these things, and they're going through their safety license procedures and so on and so forth. So we still don't know what's going to happen. All right, I think I'm going to stop there and pass it on to Eric. Thank you.
Okay, I'm going to give you a crash course in electricity generation technology and the electricity system in New Jersey. And I'm trained as an engineer, and I like numbers, so there's going to be a few numbers on the screen here. Hopefully the study guide questions will help you through the important points here. So I'll talk about electricity generation in New Jersey. I'll talk about different technologies for generation, and you'll see that I include nuclear, renewables, fossil fuels, and use efficiency as a generation technology. So efficiency is another way of getting electricity in a sense, because we can get more for every kilowatt hour. And then some of you may have heard about the term smart grid, and I'll talk about that at the end. So first question, who wants to guess how much electricity we get from nuclear in New Jersey? Any idea? How much? 1/3, 20? 40? 17? Do I hear 50? Anybody 50? All right, how about 55? How about 55? All right, 55% of our electricity comes from nuclear. That's a pretty large number, and we're trying to talk about what we're going to do in place of that. Natural gas is the other big energy source. Coal is the third. Renewables, solar, wind, and so on is about 2%. Okay. So just to, again, some numbers. In New Jersey, we generate about 62 terawatt hours. That's 1 billion kilowatt hours is a terawatt hour. Average house uses about 9,000 kilowatt hours a year. New Jersey is not the highest nuclear state. Vermont is about 2/3 of its electricity, although that may change soon. New Hampshire and Connecticut are about the same as New Jersey. South Carolina and Illinois have about 20%. For the U.S. as a whole, it's about 20% nuclear. Other countries, Japan before the accident was 24%. European Union is average of 14%, but that's going down a little bit because of what Germany is doing. But there are some countries like France where it's 70 or 80% of the electricity generation. The Brazil, China, India, the developing countries are small fractions nuclear today, but you might have noticed in one of the charts that Alex showed, China has big plans for expansion of nuclear. Of course, the big benefit that we've talked about already for nuclear is low CO2 emissions. These are New Jersey's CO2 emissions since 1990. You can see most of it today is from gas, natural gas, and coal. Coal doesn't generate a lot of our electricity in New Jersey, but it has a disproportionate carbon emissions because the amount that you get for every kilowatt hour that you generate is a lot higher with coal than with natural gas, about twice. So 1,000 kilograms of CO2 per kilowatt hour for coal. Nuclear, solar, wind, essentially zero by comparison to the fossil fuels. One term you may have heard about is the talk about shale gas. Has anybody heard that term? Okay, a couple people. Shale gas is a new discovery, a relatively recent discovery, that there's a lot of natural gas that's trapped in shale rock that is deep underground, and if you go in and fracture the rock, you can get that gas to come up. And this shale gas is sort of pervasive. It's in a lot of the different rock around the country, and people are talking about that as a almost inexhaustible supply of natural gas, which is attractive because it's low carbon relative to coal, or so we think. But there's some analysis that suggests that shale gas, when you do the extraction of the gas, you release a lot of methane to the atmosphere, and methane is a powerful greenhouse gas. And so it may not be as clean as the natural gas that we have been using for the most part. The other environmental impact of fossil fuels is not the carbon side, but on local pollution, in particular small particles that are emitted by coal-fired power plants. And even what are called clean coal-fired power plants will emit small particles that get into the lungs and cause health damages. The estimate is that something like 24,000 people a year die prematurely in the U.S. because of air pollution from coal. And just for comparison, the estimate for number of people who died at the Chernobyl accident was about 10,000 total for nuclear power. 24,000 a year die prematurely in the U.S. from coal-fired pollution. You can turn that into an extra cost of coal if you put some value on a life. And the estimates, this is from a National Academy study, 3 cents a kilowatt hour extra cost just because of the damage that comes from health impacts. And I'll put that number, that cost number, in a bit of perspective a little bit later. Okay, so let's run through what alternatives there are to nuclear and high carbon fossil fuels. Starting with biomass, this shows how much biomass, that's plant matter, that grows or that's available per square kilometer in the US. In New Jersey, we don't have a lot of land, and you need land to grow biomass, so the conclusion is we don't have a lot of potential for biomass electricity. One estimate is about 10% of our current electricity generation we might be able to do with biomass. Solar, photovoltaic solar panels, you've probably seen them up on the telephone poles that are going up around New Jersey. The solar resource in the US or in New Jersey is relatively modest compared to, for example, the southwestern US, where it's much stronger. The estimate in New Jersey is an average solar installation, that is solar energy coming into the ground, about 3.5 kilowatt hours per square meter per day. And if you go through the math and convert that at about 10% efficiency into electricity, which is easily doable today, you get about if you covered 3% of the area of the state, you could generate as much electricity as we use today, which seems like a small number on the one hand, but if you think about finding that kind of land area in New Jersey, not only is it hard to find the land area, but it's expensive land for the most part. And in fact, the electricity is only available when the sun shines, so it doesn't do you that much good unless you have some storage capacity so that to be able to use it at nighttime, for example. And on top of that, electricity from solar is very expensive today. I'll show you some numbers later on that. So if you have expensive electricity and you want to add storage capacity to that, that's even more expensive. So solar is somewhat limited. The wind resource in the US, most of it's in the Great Plains. It's called the wind belt down the middle of the country. New Jersey looks like it's relatively modest wind resource as well compared to the rest of the country. But what the rest of the country doesn't have, and New Jersey does, is the Jersey Shore. And not the TV show, right? And you guys have been to the shore, you know how the wind blows down there probably all the time. And the resources there are considered good to excellent offshore, not on land, but offshore. And this is one estimate by the National Renewable Energy Lab that shows where the wind potential is. They estimate that there's about 100 gigawatts, that's 100 million kilowatts of capacity, electrical generating capacity. And if you were to be able to build that many wind turbines, you could generate 4 times the amount of electricity that we use in New Jersey today. But what's the problem with this? Sorry? It's not guaranteed. Somebody say cost? Yeah, the wind doesn't blow all the time, and in fact we don't know when it's going to blow. So you have to have storage again if you want to have a reliable electricity supply. Cost, wind energy is actually less expensive than solar, but it's still more expensive than conventional alternatives. And the last issue is aesthetics. Some people don't want to see wind turbines off the Jersey Shore because they feel they're unsightly. And this is a public perception issue that Ramana was talking about with nuclear, but it's there for wind as well. And this is a project off of Atlantic City that's been proposed, and this is on this company's website. You can see what 15 miles off the coast is what they're proposing. You can almost see the turbines there. With your eyes, you can probably see them. With mine, I can't quite see it. So that's an issue that has to be dealt with wind. Okay, so one other option for low carbon electricity is to take fossil fuels, extract the energy from them to make electricity, but then capture the CO2 and bury it somewhere to keep it out of the atmosphere. All right? And there are technologies for doing this. You basically separate the CO2 from the rest of the combustion gases at the plant, and you pipe the CO2 to a point where you can inject it below ground and have it stay underground. And you can get a 90% reduction in CO2 emissions with this. And as an added benefit, you get 100% reduction in other emissions like the small particles. So there's a health benefit that comes with this as well. And there's one project that's been proposed in Linden, New Jersey, which is going to make electricity and chemicals from coal and take the CO2 and pipe it to a point about 70 miles offshore and put it under the floor of the ocean into a geologic formation there that would keep it permanently, essentially. So this idea is being worked on a lot. There's a big program here at Princeton that's working on this concept of CO2 capture and storage, but it's probably a decade or more away before you're going to have it routinely available because there's still some bugs to work out with it. All right, but it's a potential option in the longer term. So let me change gears and talk about a little bit how you put all these resources together in an electricity grid. This is the top black line on this graph is how much electricity the whole sort of, let's say the state is requesting everybody in their houses and their office buildings and industries. That's how much electricity you need to supply. And this is over the course of a day. You can see at nighttime the electricity demand goes down. In the middle of the afternoon, maybe it's a summer afternoon and the air conditioners are coming on, you have a peak load there. And you have the blue section is what's called base load. That is electricity you want all the time to be there. The green is called intermediate load, where sometimes you need it and sometimes you don't. And then the small orange is called peak load, which is just a few hours a day or a couple hours, and maybe even just an hour a day. You need a certain peak amount of delivered electricity to meet all the loads. That's the traditional electricity generation model. Now, if you try to put renewables that are variable, like wind and solar on this, and there is potential for that in New Jersey, you get a picture that looks something like this. On the upper left is sort of without any wind power, or let's say variables, renewables, and this is now looking over the course of a week. So each of those little peaks is one day, and on the vertical axis is how much power you need to supply to the whole system. Now you start adding wind, 11% renewables there, and what you do is you start backing off natural gas, and that's okay. You're reducing carbon emissions and so on. And as you build up the amount of renewables, if you go to the case with 35%, so roughly a third of the electricity there is coming from the wind, and you say, I want to take the wind electricity whenever it's available, and when it's not available, we'll burn coal in the gray, for example. And if you do that, what you see is that the coal plants are now, you need a certain level of coal plant, but at certain times you need a lot less coal. All right, so what you're doing essentially is running coal plants up and down. And the same with, in this case, nuclear is at the very bottom. Most of those are running pretty steady. But coal plants, nuclear plants, both of them take a long time to start up and shut down. So coal plant, I took my class to visit a coal plant in Trenton a couple days ago, and they told us that it takes 16 hours to start up the plant, and probably comparable to shut it down. And so you don't want to be turning it up and down all the time. It leads to problems with the equipment, potentially more wear and tear, more risk of accidents, and so on. And so that's true of baseload technologies. You want them to run all the time. And so this is an issue. If we want a lot of renewables in the system, we're going to have to deal with this kind of a problem. Okay, so let's look at a quick look at costs. This is a study that was done by the National Academy of Science that compared a lot of different technologies, and there's a big range of costs on all of them because there are specific situations and specific technologies. It's hard to be precise with just a single number. And what you can see for nuclear, their estimate is anywhere from 6 to 13 cents a kilowatt hour is the cost of generating electricity. For coal, you're down at 5 to 9 cents. And remember, if you add the damages from health that I said were 3 cents roughly to that, you might get the real cost of coal. Natural gas, which is NGCC, that means natural gas combined cycle. There's a high version and a low version. That basically refers to the natural gas price that you're paying. Today, we're closer to the low version, so natural gas is actually a fairly attractive fuel from a cost standpoint. If you add carbon capture and storage, as I discussed, look at the two coal and coal CCS. you roughly double the cost of generating electricity. Okay? So any of the options in that upper graph that you want, low carbon emissions, so nuclear, coal with CCS, natural gas with CCS, biopower, but there's not a lot of that in New Jersey, is going to be fairly expensive power. On the bottom are the renewables, wind and solar, and these are intermittent, so you can't compare them directly with the numbers up above because the numbers up above are very reliable electricity there all the time. The numbers down below, you see offshore wind, which is the potential for New Jersey, anywhere from 5 to 18 cents a kilowatt hour. You have to look carefully at the resource and the specifics of the situation. But in general, it's fairly expensive electricity, but not as expensive as the solar PV, which is photovoltaics. So those are some cost numbers. These numbers here are for plants that are new. So this is looking forward. It's how much it's going to cost you to make new types of electricity. Once you build a plant, like the Oyster Creek and Hope Creek and the plants that are existing in New Jersey, then what you do is look at what it costs to actually run them. You forget about how much it costs to build them. You just look at what it costs to run them. And by that measure, nuclear is the cheapest source of electricity. Coal is next because coal prices are pretty low compared to natural gas, and natural gas is in the middle. So this is the way electricity power plants would be dispatched. That is, they would be turned on as the amount of electricity that's required in the system goes up. You turn the plants on one at a time, starting with the nuclears, and then coal, and then gas. And so you're essentially running your nuclear plants all the time because they're the cheapest ones to run. All right, the last electricity source I'll mention is energy efficiency. All right, or reducing the amount of electricity that you need to provide the same service. This is an estimate of the carbon dioxide emissions from different sectors in the U.S. And what's interesting here is that the orange part there is carbon emissions associated with electricity that gets used in the residential sector or the commercial sector, and that's mostly in buildings. So lights and video projectors and computers and everything else that goes on inside a building accounts for most of the electricity that's generated in the U.S. So if you look at what the electricity savings potential are in buildings, you get this kind of graph that shows on the vertical axis it's what it costs you to save electricity. So, for example, if you have an air conditioner and you want to if you buy a more efficient air conditioner, you're going to save some electricity, but you're also going to probably pay a little bit more for that extra efficiency. It's going to cost you more at the store, and that extra payment has to be made up by the savings in reduced electricity consumption. And that's essentially what that vertical axis is, how much more it's costing you to save each kilowatt hour. And these are, you can see all the different applications, color TVs, lighting is a big one. Number 10 is space cooling, that's air conditioning. And all of the costs per kilowatt hour to save electricity, you can compare that against the dashed line up above, which is the average price of electricity to residential customers. It's much higher than what it costs you to save. So that says it's very economic to save electricity. This is an estimate for the US as a whole. So 600 terawatt hours of electricity roughly over this range that's shown. If you translate that to New Jersey, this is a very rough estimate, but New Jersey generates about 1.5% of all electricity that's generated in the US. If you assume that same fraction of electricity savings from this estimate that was made here, that's about 9 terawatt hours of electricity. So that's about 15% of New Jersey's current electricity generation. Potentially you could save in the residential sector just by becoming more efficient with electricity use. Similar kind of graph for the commercial sector, commercial buildings. And if you run through the numbers, it comes out that if you add the last bullet point there, if you add residential and commercial savings potential in New Jersey, it's about 1/3 of what we currently generate we could get away without using and not suffer any less comfort in what we use the electricity for. So it's a pretty big potential, and it's very economic compared to continuing to buy electricity. And there's a good example in California where this has had a big impact through policies that were implemented at the state level. This shows the amount of electricity per year that was saved, is estimated to have been saved because of energy efficiency improvements. And the 3 different policy measures that were implemented are appliance standards, that is requiring manufacturers of refrigerators, air conditioners, and so on to meet a certain minimum efficiency. Building standards, when you build a building, you have to have a certain energy performance or you don't get a permit to build it. And then the last one is an interesting one, electric utilities. The traditional model is you sell electricity and you make money, but now you're asking utilities to not sell electricity, to sell less electricity and still make money, and they figured out a way to do that programmatic policy-wise in California. And so over this was a long period, it's about a 30-year period, 15% of annual electricity use was saved in California. So it's an effective tool, but it does take time to implement, but it's very cost-effective as well. Okay, just to finish up, what I haven't said about New Jersey is that New Jersey electricity generation system is part of a broader network of generators around neighboring states called PJM. Pennsylvania, Jersey, Maryland, I think was the original name for that. And so there's an opportunity to trade electricity with these other states. It turns out that the distribution of power generation in these other states is largely fossil fuel. Coal is 50%, gas is 10%, and it's about a third nuclear as well. So there's not a big benefit in terms of going to lower carbon, for example, electricity by trading, but there is a potential. There are these what's called these interconnections, different regions in the country that we could trade with. And if you look at the Great Plains, the green interconnection here, that's where most of the wind power potential is, for example. And if you have long-distance transmission lines, could bring that wind power from the Great Plains to the East Coast. That's a possibility. That capacity doesn't exist today to do that. You'd have to build new transmission lines. So the last slide, the idea of new transmission lines, of using energy efficiency, of using variable wind and solar resources, you put all that together and you get what's called the smart grid. So on the traditional electric utility model is you have generation going on one side of the fence, you have somebody who's asking for electricity on the other, and you just supply that electricity. The smart grid is where you combine all of these different resources in clever ways, and you coordinate that with what's going on the demand side. So, for example, demand on the lower figure, the demand block is just the conventional, I want electricity for my TV, let me have it. Demand response refers to giving information from the supply side to the user so that they can adjust whether they want to turn the TV on when they're paying 25 cents a kilowatt hour for electricity at some peak time, or they can wait till the prices go down and TiVo their show and watch it later. So that's demand response. Energy efficiency I've talked about. You could put solar panels on rooftops, which again is relatively expensive, but it can help with the overall electricity supply. And the last one up at the top there, plug-in hybrid electric vehicles. There's big batteries on these cars. If you're not driving the car, you could potentially plug that into the grid and send electricity back to the grid when it's needed. And the idea of the smart grid is to coordinate all of these in a way that maximizes efficiency and minimizes cost. There's a lot of infrastructure development that has to happen for this kind of a smart grid to evolve. So it'll take some time, but that's sort of the one concept of the future of electricity. That's it.
Can everybody hear me? Can people hear me? Okay, good. Well, I'm last but not least, And I'm going to take a little slightly different tack than the previous speakers and talk more broadly about leadership, about crises in general, and then follow it up with nuclear reactor accidents in particular. Yeah, can you just go to the next slide? Thank you. So here's my outline. Talk about leadership, structure of the U.S. government, what's a crisis. Talk very briefly about Hurricane Katrina, because it was really a devastating crisis in this country. And then talk about nuclear reactor accidents. So what makes a leader? I have some pictures of some political leaders up here. Does anybody have any ideas what a leader is? Any thoughts? And we elect them, but what do? What makes a leader? Yeah?
Like the ability to determine like sound policy decisions from like a national standpoint and to enact them and implement them in the world.
Okay, good. Anyone else? Any ideas? Yeah.
Ability to organize a large group of unorganized people.
Okay, good. Yeah.
The ability to make decisions in a short span of time.
Okay. Let me ask you guys a question. How many of you are heads of a club in your high school? Can I see a show of hands? How many of you are captain of a sports team? How many of you are like the editor of the school paper? Okay, well, you guys are all leaders, because that's what leaders do. In essence, a leader is somebody who can make something happen that wouldn't happen otherwise. You step above and beyond your comfort level, and you make decisions for the benefit of others, fundamentally. So you can have a leader of a family, leader of a troop, leader of a community, leader of a company or an organization, all the way up to a leader of a country. So leaders are extremely important, and I hope my talk will illustrate that. Yeah. So when this country was founded, the writing of the Constitution, the founders established 3 branches of government. Next slide. We have the legislative branch, the executive branch, and the judicial branch. Which branch do you think is the one most responsible for responding to a crisis? Which is the one that's in the bullseye of making decisions? Right, the executive, very good. So here we have at the federal level, we have our executive, which is the president. And I don't have a laser pointer. He's the one who sets policies and makes decisions in regards to a crisis. Now, he obviously can't do everything, so he has to have appointees, appointed officials. And up at the top is, thanks. Up at the top is Secretary of Health and Human Services, Kathleen Sebelius, former governor of Kansas. She is his appointee. So she makes set policies for that bureaucracy, and that bureaucracy oversees a number of other agencies, one of which is the Centers for Disease Control, currently headed by Dr. Thomas Frieden. So the political leader sets policies, often doesn't make these decisions in a vacuum, but gets advice from experts. And these are the folks who carry out these policies, okay? Next slide. So that's at the federal level. At the state level, we have our illustrious Governor Chris Christie, who we all know and love. Acting commissioner. Now, he's got a couple of acting commissioners. And I believe, actually, this individual is now just been appointed commissioner, acting commissioner of Health and Senior Services, acting commissioner of the Department of Education. So he's got acting commissioners. Acting means they're filling in until he appoints somebody more permanent. Next slide. And at the local level, in, for example, the city of Trenton, you've got the mayor, who is the elected official. And I could not find a director of health. You've got an acting director of police. Now, what's some of the challenges if you have an acting appointee in a crisis? Anybody have any ideas? Yeah.
They might not be viewed as having as much legitimacy as somebody else.
Yeah, exactly. And in addition, they might not have developed a relationship to know what each other's thinking if they're acting or just filling in. And so that's a challenge. So ideally, for an effective elected official, you don't want to have either an absent position or an acting. You might get away with it in day-to-day life, but in the times of a crisis, it can be a real problem. So here at the local level and even at the state level, having acting appointees is a problem. And you don't want to have that when you have, for example, a nuclear reactor accident. Next. So what's a crisis? I got some pictures here of some crises. What is a crisis?
Something bad.
Something bad, yeah. Yeah.
Something that provokes the desire for a change of quality of government.
Sure. Anybody else? Yeah.
It's something catastrophic, something unpredictable, or something that results in severe loss to either property or human life.
Right. So good. So great answer. You can have a societal crisis, which is what I'm showing you here. You can even have a personal crisis. You can get into a car accident. That's a crisis, right? But for the sake of this talk, we're going to talk about societal accidents. This is unfortunately a terrorist attack. That was a man-made crisis. But many of the crises that we deal with are from Mother Nature. But you have to be prepared for all. If you're an elected official, you are responsible for the health and safety of the people living within the jurisdiction to which you were elected. Yeah. So let's just briefly talk about Hurricane Katrina. That happened in 2005. That was a devastating crisis. Next slide. And they got advanced warning. So the elected officials at that time, at the federal level, we had George Bush. He was president. At the state level was Kathleen Blanco. And at the local level was the mayor, C. Ray Nagin. Did any of them take charge? That's the big question. Next. We had appointed officials. The appointed official at the federal level of Homeland Security was Michael Chertoff. Michael Brown was head of FEMA. And in New Orleans was State Police Superintendent Edwin Compass. Next slide, please. Part of the challenge there was that there had been, for many years, warnings that New Orleans really was not prepared for a hurricane. And the planning was minimal at best. They had an evacuation plan that was reportedly a page and a half long. There's questions as to whether or not anybody actually even read it. They did not coordinate. When you've got federal, state, and local officials, they all have to coordinate with each other to know what they're doing. Part of the other challenges with Louisiana is it's got 64 parishes. Each one has a president, and they apparently did not talk to each other either. Crises do not recognize political borders. And the more political borders that you have, the more challenges that you face with communication and coordination, not only horizontally across, but vertically as well. Next. New Orleans is below sea level, so it's basically a cup floating in a lake. Next. And so what happened in this crisis was wind and water. We had broken levees that were old and dysfunctional. Next. And massive flooding. Next. Next. It's just devastating. Next. Damaged property. Unfortunately, thousands of people lost their lives. FEMA had recommendations that it takes about 3 days to evacuate people out of a city, often requiring school buses. The school buses during Hurricane Katrina sat unused, and a lot of people drowned. Next slide. So this is an example of failureship at the federal, state, and local level. So when elected officials and appointed officials are not doing their jobs, people die. And this is really serious business. Next slide. So let's talk a bit about nuclear reactor accidents. What are the dangers? There's been some brief discussion by the previous speakers. What leadership would be needed during a nuclear reactor accident? What would the political leaders and appointed leaders have to do? What decisions would they have to make? And finally, what's the situation here in New Jersey? So we've talked a bit, or you've heard a bit, I'm sure, about what happened in Fukushima with the massive earthquake followed by the tsunami, and Chernobyl. Both of these were classified as 7 out of 7 nuclear disasters. Next. The effect by Chernobyl, you saw this already. Massive widespread contamination by radioactive materials. Next. 3 Mile Island happened here, in Pennsylvania in 1979. This, as was mentioned previously, was not from a natural disaster, fortunately. It was a stuck valve followed by human error that they didn't recognize that this problem existed, and they lost some coolant and released a substantial amount of radioactive material, but fortunately not into the environment. So we kind of dodged a bullet on that one. Next. But what are the health risks? Now, everybody's scared about radioactivity, but what exactly are the health risks? Why are we concerned about radioactivity? Well, there's two compounds particularly that we're most concerned about in a nuclear reactor accident. One is cesium-137, which has a half-life of 30 years. So once that gets out into the environment, that's there for quite a while. And it releases penetrating gamma rays, which can damage our DNA. Our DNA, animals' DNA, which is not good. And I'll discuss that in the next slide. The other radioactive material that we're concerned about is radioactive iodine. That has a half-life of 8 days, and that affects primarily the thyroid gland, which I will talk about in a subsequent slide. Next. So radiation sickness is one of the major concerns with cesium. And as I said, it damages the DNA. And what happens is, if you get a large enough dose, it will affect the cells that are most rapidly dividing. The cells in our bodies that divide the most quickly are those in our GI tract and our hair. So you will have symptoms associated with that, including nausea, vomiting, and diarrhea. And it's not a surprise that people who get chemotherapy, which is targeted against cancer cells as well as the rapidly dividing cells, get nausea, vomiting, and diarrhea. Fortunately, we have drugs that can counteract some of those side effects. But the person loses their hair, and they're feeling pretty bad. And unfortunately, if the dose is large enough, like about 6 grays, which is about 6 million times what you would get in a chest X-ray, you will die. Massive amount of radiation, they can die within 2 weeks. Next slide. So what's the strategy to avoid acute radiation sickness? There's only one. Get out of there. Evacuate. That's the only thing that you can do, is to evacuate. Now, the challenge for an elected official is you can tell everybody to evacuate, as they did with Hurricane Katrina. It's one thing to order, it's another thing to actually carry it out. So you have to have plans in place on how to actually do this. So you need to recruit school buses, you need to get people, there are plenty of people who have cars and the wherewithal to evacuate themselves, but there are plenty of people who don't. Particularly those who are poor, who might depend on public transportation. And where are they going to evacuate to? You can tell them to evacuate. Well, that's great, but where are they going to go? So these are all things that elected officials and their appointees need to figure out ahead of time. So evacuation is an important strategy. Next. Let me talk a little bit about radioactive iodine and your thyroid gland. The thyroid gland is a butterfly-shaped gland at the base of your neck. Might not think about it too much, but it's actually critical for you to live. What it does is it traps iodine that you usually get in your food, and converts it into thyroid hormone, which regulates the metabolism of your body. So, for example, your heart rate, your metabolic rate, all of this is dependent upon your thyroid hormone. There's a disease called Graves' disease where the thyroid gland starts pumping out too much thyroid hormone, and you start getting rapid heartbeats, and your eyes start bulging out. It's not good. And you cannot survive if you have too much thyroid hormone. You cannot survive if you have too little thyroid hormone. Next. So the strategy to avoid, actually go back a little bit. Thyroid hormone, I have to also say, is extremely critical for infants, for newborns, and for young children. Newborns get a burst of thyroid hormone that's critical for mental development. And if they don't get that, then they are permanently damaged for the rest of their lives. So any kind of strategy to mitigate the effect of radioactive iodine has to be targeted towards children. Now, what happens in a nuclear reactor accident is not only a cesium release, but also radioactive iodine. And what happens is the plume comes over and will fall down into the ground, and most people will get it through food. So, for example, cows will eat the grass that's contaminated, produce radioactive milk, and children will drink radioactive milk. And you see some of this in Japan. They've detected some radioactive food, radioactive water, and you have to make sure that people don't drink it. So in addition to avoiding those kinds of things, the other strategy, next slide, is potassium iodide, which is basically an inert salt. So if you ingest that right before or immediately concurrent to when this radioactive plume is going by, it can block your thyroid gland from uptaking the dangerous radioactive stuff. But it has to be timed properly. So you can get that, you can purchase that on the internet. So you want to make sure that pregnant women, young babies, and children in particular, young adults like yourselves, get this get the potassium iodide to block your thyroid gland from taking up the radioactive stuff. And in addition, you want to ban fruits and vegetables and milk that are potentially contaminated with the radioactive iodine as well. Now, so since potassium iodide is so important, part of the planning challenges is, well, who do you give it to? And how many people get it? So there's some challenges that we have at the federal level because the Nuclear Regulatory Commission that oversees this has regulations requiring that people living within 10 miles of a nuclear reactor be given potassium iodide. But on the other hand, the Public Health Security and Bioterrorism Preparedness and Response Act of 2002 requires that potassium iodide be available within 20 miles of a nuclear reactor. So here you've got two competing regulations. And what do you do? Is it 10 miles? Is it 20 miles? Who do you give it to? And who's going to pay for it? And how do you make this decision? Next. So this is a policy dilemma for an elected official, particularly at the state level. You saw the map, and I have one in a subsequent slide, that New Jersey is essentially ringed by nuclear reactors. We have 4 within our borders, and we have 6 within 50 miles of our borders. And if there is a crisis and one of them releases this material, well, how many people should be getting potassium iodide? And it's not necessarily, and we saw with Fukushima, and even with Chernobyl, that the amount of radioactivity can spread for miles, far more than just 10 or 20. So how far do you go? I mean, you could argue that basically everybody in the entire state should get it, but then who's going to pay for it? So some of the decisions that leaders need to make. in the event of a nuclear reactor accident, you have to decide when to evacuate, where to evacuate to, potassium iodide distribution, how many people get it, and how far. How are you going to get uncontaminated milk and food to people without access to the poor, especially infants, women, and pregnant women and children? And what about long-term planning on this? Again, this is the situation in New Jersey. You saw basically the entire state is ringed by nuclear reactors. So this issue is of particular importance for us. Next slide. So the take-home points that I'd like you to remember is one, that leadership is really important. You want people who take these issues seriously and who can do advanced planning. Ultimately, the elected officials are in charge. Whether or not they have qualified appointees in place to carry out their policies can have a huge impact on how many people live during a crisis. The relationship between elected officials and appointed officials are critical. Ideally, you do not want to have appointed officials who are acting, who are just holding, placeholders until somebody is appointed. And even worse is an absent or vacant position, because then you don't have any appointed official in place making decisions and carrying out these policies. So the leaders must have the health, safety, and well-being of the people within their jurisdiction their highest priority. Next slide. Take-home points again in terms of nuclear reactor accidents. I can't stress how important it is, the issue of evacuation and potassium iodide. These are the two most critical decision-making issues that leaders must make. And that's it. Thank you very much.
So we have about 15 minutes for some questions. You can ask them from your seat, just be sure to ask it loudly. But this is your chance to think of all the amazing information you got and see if there's anything you need to clarify before we break out.
What's the cost of building a nuclear power plant, and how does that compare with the cost of building a solar plant or a coal plant, another plant that uses the same amount of electricity?
Well, Eric had the slides, I guess.
Yeah. So a nuclear, we don't really know what it costs to build a nuclear plant because we haven't built one in 30 years in this country. The estimates are, it probably, you guys can check me, but $8-10 billion for let's say a typical size. If you try to produce that much electricity with solar, again, there's the problem that the solar isn't the same kind of electricity because it's variable, but it's probably going to cost you a similar amount of dollars.
Eric, you showed the levelized cost of electricity. I mean, these bands on his slide, and it showed that nuclear was between, I think, 8 and 13 cents a kilowatt hour. That's basically the price you have to charge for the electricity you pay for your power plant upfront. So essentially, it's equivalent to the price of building the power plant in the first place.
Some people said that the power plants were old. Like, where would the money come from to make them new?
Yeah. Well, the way it would work is that the operator of the plant has to, and you guys can correct me, but in New Jersey, the power plants are owned by PSE&G, which is a private company, and they make a contract with the utility grid to sell them electricity at a certain price. Right. So if they want to improve their plants or build new capacity or something, they have to be able to collect that money from the customers, basically. So the customers ultimately will pay for it.
And if I may add to that, conversely, with the plants that are already there, which is sort of ending their lifetime, so their 40-year lifetime, if they decide to run it for a longer period of time, then it's essentially all profit to the utility because they already recovered most of their costs. So it's only the cost of running the plant that they have to sort of recover at this point, the cost of the uranium and the cost of paying salaries to the operators. And that's a very low fraction for nuclear power.
When would an area that's been irradiated become safe for people to move back into after the evacuation?
So Laura mentioned this compound called cesium, which has a half-life of about 30 years. And much of the regions around Chernobyl that you sort of saw, those red spots and so on, are graded with respect to how much cesium has been deposited on the ground. So cesium is a gamma emitter, so sort of walking around there, you're going to get radiation dose. So this takes about 30 years to decrease in half, to half the radioactive level. So you would probably say, several times that, maybe 10 times that, so 300 years is sort of the time. But it won't be 300 years because over a period of time, what happens is soil sort of settles down, other things come and fall on top of it. So you probably think several decades, maybe 100 years. Order of magnitude. Yeah.
But of course, you can do decontamination. I mean, in principle, you can do something against it. It's just very expensive. Yeah, we see many hands. It's very hard. Maybe you should just speak up.
Comment on the effectiveness or efficiency of long-distance transmission lines. Are they more effective than locally produced energy?
If you're transmitting electricity long distances, you're going to do it at very high voltage so that you don't incur as much loss in the transmission. And they're quite feasible. There are long-distance, high-voltage transmission lines around the world in different places. It just takes money to build them.
But it's also difficult, I guess. People don't like nuclear power plants, but they also don't like transmission lines, I guess.
Yeah, exactly. People worry about being close to a high-voltage transmission line because of what effects it might have, and there are studies on that. I don't know the results of that.
You stated that one of the problems with renewables, with wind and solar, was the variability factor, but you also stated that it would be possible to produce several times more energy than we actually need. So if it was storing that energy, that would not actually be a factor, or would that just be so unfeasible that it would still be a factor?
No, you can. There are ways that you can store electricity, and that would be a way to do it, but it's going to be more costly. And the renewables are already more costly today, even without the storage. So it's all a matter of cost.
In the back there?
How would a new power plant affect the price of gas in our state or country?
What kind of gas? The gas that you put in your car or natural gas?
A car.
They're very loosely coupled. You don't use a lot of gas for generating electricity. So unless you have a large number of electric cars and so on, it's not going to really have a huge impact.
Not even the ban on oil?
There's very little oil used for power generation in the U.S.
They're absolute oranges.
I'm going to challenge you guys. I've only heard from males. Females, talk. Okay. No, not talk that way. Ask questions. Okay, great question.
What about energy from water sources or the ocean? Is that even coming into effect? Is that helpful at all, or is that even possible? Because I know that I heard there was new technology where they would put something in the ocean and it gets the energy from the waves to keep going.
Yeah, there's wave energy, there's ocean thermal, where you use the gradients in temperature in the ocean to generate power. All of those are going to be more expensive than the options that we were talking about here.
Could you say again how the annual deaths caused by the particle emissions from the coal compared to the deaths from Chernobyl?
They're different estimates, but the number that was in an op-ed that one of our colleagues published a couple of weeks ago was 10,000 deaths from Chernobyl, And his number was 10,000 deaths from coal per year in the U.S. My number is more like 30,000. So there's a lot of uncertainty in it, but comparable numbers. But this is per year for coal versus total for the.
Could you speak a little more as to like how the smart grid works? Like, you know, has anything that has been implemented?
I'll give you one example. It's in California, you can buy a device that you put into your electric socket, and you dial in the price you're willing to pay for electricity coming out of that socket. All right, so you plug your air conditioner into it and say, I'm willing to pay up to 20 cents a kilowatt hour, and dial it in, and there's a connection between that device and wirelessly to the utility. It says when it's more than that, I'm going to cut the power to this. That's an example of one device.
What are going to be the widespread effects from a nuclear meltdown
Nuclear meltdown where?
in Japan?
Most of the effects are going to be sort of close to the power plant, the places which are being evacuated, for example. So many of those areas will have to be evacuated for a fairly long period of time. We still the accident still isn't done in some sense. There's still stuff coming out, so we don't have to. We have to sort of wait on trying to predict how long and how much of that area is going to be there.
And the Japanese have been really lucky for the first days when the wind was really blowing away from the island not towards Tokyo. It could have been, more serious than it turned out to be.
For health effects, they've been pretty effective in administering potassium iodide, but for those who didn't get it, particularly children, they are at risk for getting thyroid cancer from ingestion of the radioactive iodine.
Hi. Is there any way that the radiation would be able to, is there any way that the radiation will reach us in New Jersey anytime soon or possibly in the future?
You mean from Japan?
Yeah.
At very small levels, at essentially negligible levels.
And why has the industry been reluctant to implement dry cast and form disposal of radioactive waste?
Oh, it's a real pro question. Well, it's a good question. I guess if we understand correctly, we're asking about dry cast storage. So every year you discharge, 20 tons of spent fuel from a reactor, and first you kind of move them to a pool, which is what happened in Japan. But at some point you can actually move them into just not ordinary, but dry casks. And really, I think the only reason, that's a good thing. It's a safe and simple way to store nuclear waste, at least for 100 years or so. But the problem is you need these casks. Utilities have to be willing to invest, the money to purchase these casks. And I think there will be a strong push in the U.S. especially to kind of do this. And we'll see the NRC will come out with a report soon. And I suspect, or I predict there will be a recommendation to move very aggressively towards dry cast storage.
Are you each personally for or against the use of nuclear power?
Now, they were told not to bring opinions into this. We're just giving you facts, but I'll let them give their ideas.
Well, there's one line that we often use. We are anti-pro.
I think that sums it up. Anti-pro.
These guys are researchers. Okay, in the back, we're going to take about 2 more.
Okay.
Yeah. And then how about you and then the other person in the back?
If the radiation can damage DNA, can those damaged DNA be passed down?
If the DNA that was damaged in the germline, yes, potentially.
Yeah, the answer is we've seen this in many cases in the case of things like fruit flies, which are very short generational periods, so there's no doubt that biologically this is something that's going to happen. It just seems to be observed at a very low frequency in the case of human populations.
Okay, we still have questions, right here.
Hi, Mr. Larson, in your presentation you stated that nuclear power plants are expensive, and I wanted to know if they would be less expensive and more effective to use of alternate sources for energy, or is it lost?
I would say it's going to be a wash, about the same. But it's very uncertain what the nuclear plants actually are going to cost. It depends how much regulation is put on top of it. If you have to have lots of safety features that we don't have today, for example, it may drive the cost up quite a bit. Whatever we do going forward, clean energy is going to be more costly than what we've been using. So I would say.
Okay, we're going to take one more question. Well, how about two more? Red sweatshirt and the person behind you.
If within the next 10 years we're able to more effectively harness the energy from nuclear fusion reactions, how would the efficiency and safety and waste compare to those of coal and nuclear fission reactions?
Question about fusion. Well, fusion, I mean, Princeton, of course, is strong in fusion. There's the fusion research lab out there on Route 1. But I think even the most, optimistic advocates of fusion energy would argue that it's at least 40 years away. It may become, the ultimate answer to our energy problem, but it's not going to help us in the next, 40 years at a minimum. So, unfortunately, it won't help us in the problem, solving the problems we have today.
Okay, last question.
Okay, I was wondering if you could just comment about the role of public opinion, like people who don't want wind turbines because they're not aesthetically pleasing, like where does that even come from? Where would that sentiment even come from?
Are you talking about public opinion with respect to just wind or public opinion in general?
I mean, it's nuclear, but for example, I can't understand why someone would have a concern with the aesthetics of wind power because of all of the potential benefits.
You have to ask them.